Bravo, Dr. Kester. Yes, Dr. Lee?
I wonder, could you comment if the metabolized lipid or if the oxidized lipid is responsible, could the lipid itself be an immunomodulator that you could administer as a drug rather than necessarily?
You've asked a good question. I'm so glad I brought the extra slides. Go. Segue.
Okay, thank you. I'll take the answer sitting down.
I'll go to one slide. By the way, that's the derivative of the lipid. It's a ceramide. That's the Starship ceramide. We add a phosphate. We take away one of the fatty acids. That's your drug. And if we go to right there, so we've taken, here again, a cancer cell, and we've added the magic lipid, and basically we actually can take these myeloid-derived, in this experiment, we take the myeloid-derived suppressor cells, we actually purify them, we add this magic lipid, and then we actually show by flow cytometry they form into B1 B cells, and basically they'll go back into the animal. There's the growth of the tumor. So with that said, is that the therapy? Maybe. But right now, imaging and using the infrared to get imaging and the ability to do some theranostics at the same time, that's the therapy. But this could be the future therapy. You're absolutely right.
Thank you.
So can you comment on what the limits are on the sorts of other cargoes that you can incorporate? I mean, you've talked only about small molecule fluorophores. Could you do a nucleic acid, oligonucleotide, small protein, et cetera?
So, excellent question, and there are limitations. Basically, if you're a protein, forget it. We're 20 to 30 nanometers in size, and we can go as far as polypeptides. That's the limit in terms of size. In terms of what we can encapsulate, we can do small molecules from hydrophobic drugs like some of our ceramides, which are selective apoptotic agents for cancer cells, to what was being commercialized now for Keystone Nano, which is doxorubicin. And we want to see if we can make Doxil, which is a liposomal version of doxorubicin, better and have better kinetics when you put inside the calcium phosphate nanoparticle. The holy grail, you're absolutely right, is sRNA. And a lot of companies are working on liposomal technologies to deliver sRNAs, but again, you have to do that in a cationic formulation of lipids, which often leads to hepatic toxicology and or liver, and or lung toxicology. So what we've done is we can put the sRNA into these calcium phosphate nanoparticles. They have no charge. In fact, they're then highly pegylated. So you don't have the problem of cationic charge as a toxicology. With that said, we're now scaling up to get a therapeutic dose of sRNA into the calcium phosphate nanoparticle, and those are going into animals in the next couple of months.
Hi, Chris Schaffmeister, Temple University. Now, correct me if I didn't understand properly, but if you deliver these calcium phosphate nanoparticles they get into endosomes and then they release when the pH drops, you're going to be dumping a lot of calcium into the cell, which is calcium is a second messenger, which...
You got it.
What do you think the effects of that would be?
So in our first two papers, we asked those questions. Because at the end, we're using calcium phosphate. Yes, it's benign. Yes, it's used on grafts. Yes, it's used for bone grafts, et cetera. But still calcium, and it will have an effect as a second messenger. So the first experiments we did was voltage clamping. And we actually saw, then we added the calcium phosphate nanoparticles, that the cell did not change the way it dealt with the calcium. It actually pumped the calcium out as if it was seeing regular calcium, because the actual amount of calcium we're adding systemically is 10 to the negative seventh or lower. So it's a minuscule amount of calcium to the biological environment. And we've also then asked the question, well, what's the worst thing that could happen with calcium? So we said maybe atherosclerosis. So one of the first experiments we published was that we actually took an ApoE knockout mouse, added the calcium phosphate particles, 10 to the 15th particles per cc, for 3 months of therapy, and then looked at these animals that are fed a high cholesterol diet and asked what was the fat content at the aortic arch, and it didn't get worse. So those are the type of experiments that have been published to say that this truly is a biocompatible but a biobenign technology also.
Congratulations for the presentation. It was I was impressed last year. Now I'm just jealous. It's great data. Now, talking about numbers, the first experiment in which you were showing the accumulation in the tumor after the initial sequestration by the liver, how much of the injected doses you get there? And also, what is the mechanism for the clearance from the through the bile, and if there is a limitation in size? Because that's a very interesting observation.
So when we did the ADME and we started looking at distribution, for simplifying, 95% of the material ends up in the liver, 5% in the renal system, and that's pretty much it. However, it doesn't lead to liver toxicology. But even though you're lighting up the liver, it's not accumulating within the liver. It's staying in biological fluids. It's got a half-life we've calculated greater than 18 hours. Now, somehow because of the size and the true mechanism, I have no idea. We kind of alluded to this last year, that we really don't know how it's happening, but it's ending up, when we pull out and we actually image the intestine, you can see the intestine lighting up, and we've published that already. And you can, so it has to be going through the hepatic circulatory tree, through the bile, but beyond that, we don't know.
And it's not the autofluorescence of the diet. So
No.
animals are on a special diet.
Often they're not fed. That was the first question I asked. So we ran the controls without the calcium phosphate nanoparticles, without the fluoroprobe, et cetera, but we actually starved the animals for 24 plus hours, and it's not the food.
Okay, just...
And then we actually pulled out, and we actually,
And you saw.
yeah. Nasty, but we had to.
Okay, Chazi Baranolds again. Just...
And you've shown the same thing.
what?
Didn't you show that? But go on.
I'll show what you will see tomorrow. But what I wonder, based on some of the experience we have with Doxil development, quite some time ago in the late 80s, one of the important questions you have to ask in the beginning, what's the internal volume of your particle?
So this is the time I wish Jim Adair was standing next to me, because he can actually
What's the diameter?
So so we can vary the diameter depending on what we're going to load. These are 20 nanometer particles plus or minus 7 to 10 nanometers. So, and it's a matrix of calcium phosphate, and our material ends up intercalated within the nanomatrix. We have estimates when we do the fluorescence correlation spectroscopy. Our photophysicists say that we can encapsulate, they're telling us 40 molecules of doxorubicin inside one particle.
Okay.
With
Good.
the
Good
indocyanin
luck.
green,
Good luck.
I know there's a number for it, but
Okay, good luck. You will have to inject so much material that the body cannot accept.
but we're getting 10 to the 15th particles per cc. 10 to the
Okay.
15th particles per cc. So it's a million billion particles. And then actually, when we do our dosing, and we do this by mass spec, we can deliver up to 10 to the negative 4th molar doxorubicin doses. So,
Well, I tell you, based on my experience in human being, not animal anymore, but really human being, we inject 23 times in 10s in 14, which is 2.3 times in 15. We have 10,000 molecules of drug per particles, and that's about the lower limit. Right. So I think it's very, you have to go for, that's what I want to give you advice for drugs that you need much lower amount. Doxorubicin, you need 50 milligram per square meter body, which is about 100 milligram per human being, about my size. Maybe you are a little bit less. So
no, I'm getting bigger.
Okay. You know why they make the measurement in square meter? You know why?
Because more.
No, it's because we become
Bigger.
Our volume become larger, and that's why they shift to the square meter and not to the weight anymore, to take care of the fat, really.
Right.
But I'll go for something like vincristine, and that you have to give 2 milligram per much lower amount. So then you have a much, much better chance. I think that's one of the first questions you have to ask. What's the load? Can I meet it? And if not, try to find something that will work better for you.
Well, what we're seeing is when we compare ourselves, so if a dose in an animal that gives you a therapeutic dose is 10 to the negative 4th molar, we can show effects at 10 to the negative 7th molar because of the protection. So it's not, I know you're shaking your
No,
head.
doxorubicin is fully protected. We get a lot into the tumor, and still, I wish we could do better.
Yep.
And I can tell you, but it's just a kind of thing to think about for you.
Thanks.